record, we're live. Okay, so we're gonna come back to that in a second. So this is the second activity of the week. And then let's see, the Khan Academy stuff, jump in Khan Academy, play around with the active and past assignments. Okay, then we got the choose your own adventure in Polygons activity. So I had 3 or 4 more ideas for activities this week, but we don't have time to do 3 or 4 more activities. We only have time to do 1 more. So I narrowed those 3 or 4 down to 2, and you get to pick which one you do. And so I'll try to do a brief demo of each of these today. So option 1 for choose your own venture. So your first adventure option here is just playing with regular polygons. Can you use a piece of paper and a pencil and a compass and a protractor to build a good looking regular polygon? In particular here, I asked you to draw a pentagon. So that's one option. And the book goes over 2 methods for doing that. It's about 3/4 of the way through the book. They show this in section 10.2, and basically I just rewrote their instructions. And then I also added some images here of the tools in Geogebra. So if you want to try doing this with Geogebra, the reason I gave 2 options here is because some of you may not have a protractor and a compass at home, and I'd rather you not have to go out and buy one to just use it once or twice. So in that case, you probably have a computer that you have access to, so you could try Geogebra. If you find Geogebra too painful, then you might want to find somebody you could borrow a compass and protractor from. But you can usually find them cheap in like a Walmart or a Bi-Mart. So you got a couple of options there. So either you're going to draw me something on paper using a compass and a protractor like the book shows, or you're going to try it with Geogebra. And I am going to, I can't easily do the compass with the computer, but I can talk about it, but I can use Geogebra, so I'll show you that. If you don't want to do that, or you just find the next one more interesting, the book also, at the last part of the book, talks about what's called tessellation. And a tessellation is like tiling your floor. So most tiles on a floor are square, and squares are great because they fit together really nice to cover a floor. So I wanted you to come up with a more interesting tessellation. And the book, again, goes over a few examples of tessellations, like a honeycomb beehive, tessellating a triangle. They also show tessellating a quadrilateral, and then they show what are called semi-regular tessellations. They give 2 examples of those in the book. And then the homework problems after that show a few more tessellations. And then I have a link out here to a Wikipedia page with like way too many, for my mind, tessellations. So this one right here is called a regular tiling, like a beehive, or a regular tessellation, because I'm using all the same shape over and over again. Now, not any polygon will tessellate. Like try tessellating a pentagon, okay? Some pentagons tessellate, but some don't, okay? So we can take a look at that. Oops, back. And then if you scroll down this Wikipedia page I link to, they show what's called a semi-regular tessellation. And then there's all these other K-uniform type ones, and they have tons of different classifications, but some of them are pretty wild and beautiful and awesome and weird. And they go to explain a little tiny bit of the math with links to other resources. So I'm not asking you to go read through this page. This is some crazy stuff for people that specialize in studying geometry, maybe. But we could use pattern blocks to make some interesting repeatable patterns. And that's what I'm looking for here. A tessellation is a repeatable pattern that you could lay down on a floor, for example, or on a wall, or just on a piece of paper. So that's the other option for the choose your own adventure. So either you're going to build me a regular polygon on paper or in Geogebra, and then you can send me your Geogebra file or upload your picture that you drew. Or you're going to design a couple of tessellations. And actually, I meant to modify this. So this isn't quite right. Do this real quick. To make sure you got the idea about how to draw one, I wanted two examples. So a regular pentagon and another regular polygon more than 5 sides. A regular quadrilateral, that's pretty darn easy to draw. That's a square. A regular triangle is pretty easy to draw. So it only gets interesting with 5 sides and more. So I wanted you to draw 2 there. Okay, that's what I meant to have happen. And kind of to make it equal with the tessellations, because I wanted you to try 2 tessellations. I wanted you to try tessellating a single shape, some quadrilateral, that's not a rectangle, because tessellating a rectangle is pretty darn easily. I wanted it to be something more interesting. And then make a regular a semi-regular tessellation. And a semi-regular tessellation is where you try to take 2 or more shapes that repeat a pattern that you can over and over again tile your floor with. And there, if you need some inspiration, there's a ton of examples here. And then the book has a bunch of examples too, if you go to that online book and look at the end of section 10.2 and the middle of the homework assignment in the book. And if you don't know what I mean by that, ask and I'll show you. Giselle, did I remember to say hi to you? I think I did. Hi, Giselle, in case I forgot. All right, so let's go back and take a look at this activity here. So we're going to try and figure out the angle sum for a quadrilateral and a pentagon, and we'll start by playing with either the Toy Theater or the Math Learning Center pattern blocks. So I'm going to bring both of those up here. And this will involve a little bit of sketching on paper too, probably. And where's the other one? Math Learning Center. Okay, so I did the triangle one for you. My claim is that a triangle has an interior angle sum of 180 degrees because if you put the 3 angles together, you get a straight angle. And so I just want to show a picture of that. Khan Academy goes over this too. They have a video on it that you should check out. And that's the wrong page. Where did I put it? Come back to you, come back to you. I must have deleted it accidentally. My notes. There's a link to my notes page at the end of our Canvas page. And I show a couple of examples here. So I made this blue triangle on the computer, and then I made a copy of it and colored it green. And I made another copy and colored it red. So these 3 are exactly the same triangle. And then what I did is I just picked up the green one and I set it next to the first one so that it was a different angle next to angle A. Okay, so here's angle A, this is angle B. I just made a copy, picked it up and put it there. And then over here you can see this is my angle C then, and I just kind of picked that up and stuck it there. And regardless of the triangle you pick, if you take the 3 angles and you stick them together, it's always going to make a straight angle. So through this vertex point right here, those 3 angles together give me a 180 degree angle, which is also referred to as a straight angle. So this is an example of a single triangle for which the interior angles, which the book calls vertex angles, add up to 180 degrees. And you can do that in any order you want. So I kind of did it in a different order here. And this one had an interesting reason because this thing right here is kind of a funky looking shape. What kind of shape is this anyway? Let's see, there's 1 side across the top, and then 2, 3, 4, 5, 6. This is a hexagon right here. Okay? It's a concave hexagon because these sides kind of cave into the interior. Putting them over here, I get a different shape. How many sides does this have? 1, 2, 3, 4. Did I do that right? 1, 2, 3, 4. This is a quadrilateral here. And there's multiple things I was trying to get out of these 2 pictures. One is that, you know, if I put the angles CB and A together and line up those sides, I'm always going to get a straight angle regardless of the order I put them in, which is kind of cool. So that's kind of like a picture proof of why the vertex angle sum or the interior angle sum of a triangle, any triangle, is always going to be exactly 180 degrees. The reason I put them together this way is this shows a way to use a triangle to tile a floor. So if I had 100 triangles exactly the same shape and size, I could use them to smoothly tile my floor, and further down in my notes I do that. I just keep taking that triangle and recoloring it and laying them down by flipping it over. So basically I take those two triangles and I turn it into a parallelogram, and that parallelogram can tile my floor. So it turns out a square will tile a floor, a rectangle will tile a floor, any triangle will tile a floor, a parallelogram will tile a floor. A rhombus is a kind of parallelogram, so a rhombus could tile a floor. So tiles could be made out of rhombuses. They could be made out of triangles. There's lots of different shapes tiles could be where you could connect a floor so there's no gaps. You could tile a floor so there's no gaps. Okay, let's see, nothing in the chat yet. What else did I want to say about this here? Just me trying to show that the interior angle sum of a triangle is 180 degrees. So if you don't believe me and you just want to prove it to yourself, draw a triangle on a piece of paper, some random triangle, cut it out and make 2 more copies of it. So you have 3 copies. And then line up the different angles so they all meet at a specific vertex. And you'll find if you traced and cut well, then you're always going to get a straight angle where they meet. And a straight angle is where we have 3 angles together, or any number of angles really, that add up to 180 degrees, forming a straight line through the vertex. All right, so let's see. This right here, I mentioned this shape is a quadrilateral. I'm going to copy this into my workbook. Oops, that's not the right workbook. Let's make a new one. Or just delete that maybe. Delete it. No. Can I undo? Oh, there's new right there. Okay, that's what I want. All right, give me a sec. Almost there. Copy from here. So let's just review a couple of things. Add to current page. So I have 2 different shapes here. When I put these 3 triangles together, I've made a new shape. And this shape, starting right here, let's make a little mark where we're starting. Oops, and I should get my whiteboard. I'm drawing with my mouse. That's dangerous. Okay, so we're going to start here, and as I trace around, I have one side, because that's a 180 degree angle there, so that is one single side. 2, 3, 4, the angle changes there. 5, 6, okay? So this shape right here is a hexagon. So I can tile 3 of the same triangle and make a hexagon out of it. Now I could tile those in a different way down here, and if we start here on this one, we have 1, 2, 3, that's a single side because those make a straight angle, 4 through there. So this right here is a quadrilateral. Okay. We played a little bit last week with parallel lines and lines crossing through those parallel lines. So I'm just going to draw a couple other lines through this one right here to explore some ideas. There's nothing really special, I don't think, about this hexagon, although I'm probably wrong about that. Somebody could find something special in it, except it's not what's called a convex polygon. It's a concave polygon because it kind of caves in on itself there. So I should give this a better name. This, oops, that's not a pen. This is a concave hexagon. This one does not cave in on itself, so this is a convex quadrilateral. And let's draw some lines. So let's see. It looks to me like this green line up here and then the blue one down here, they seem to be parallel. So I wonder if we can show that this line right here is parallel. Put a review from last week with this line right here. So what do we know? Let's see. We've got some angle information here we can take a look at. This must be angle A right here. So there's my angle symbol A. And that's angle B up here. So angle B. And which angle is this right here, do you think? In that spot. Anybody have an idea? Let's see if that's B. This bigger one is angle A. Oh, I got a question I missed in the chat. Nobody wants to tell me what angle that is. Question in the chat is how big or to what scale does the tessellation have to be? As long as I can make it out and see it. If you make it too small, it's going to be hard to draw. If you make it too big, it's going to be hard to show on a piece of paper. So you want something that's going to show on like a 8.5 by 11 or half of an 8.5 by 11. And you just need to show enough of the pattern so I can see that it's going to continue. So we'll do an example of that in a minute. All right, you guys are not interacting. Oh, there we go. Thank you very much. Yes, that would be angle C up there. All right. Yeah, now we get some activity. So that's angle C up there. All right, so what do I know about the angles going on here? Well, if I take angle A, its measurements, and I add it to the measure of angle B, and I add that to the measure of angle C, that's going to add up to 180 degrees. Now here, I've made a new angle at the top. So let's make that red. So I have this new angle up here that's B and C combined. So let's call that angle D. So angle D is going to be grabbed by taking angle B and combining it, putting it together with angle C. So notice right here, that would be these two combined. So my new angle D is those two. So now I know that if I measure angle D and I combine that with the measure of angle A, those two together add up to 180 degrees. Now these two angles, angle D, what I'm calling angle D here and angle A, they are interior angles, okay? They're not alternate, because alternate would be on the other side of this transversal over here. So whatever angle this is over there, that would be an alternate interior. These two angles, A and angle D, they're just alternate angles. Sorry, they are interior angles because they're interior to the polygons. Interior angles are always what they call supplementary. So just a reminder, because they add up to 180, angle A and angle D are what are called supplementary. And supplementary just means, hey, they add up to 180 degrees. Okay. So if I have a pair of angles who add up to 180 degrees, that means the alternate interior angles have to be equal, congruent. So this angle out here must have the same measure as angle A, in which case that kind of justifies that these two lines are parallel to each other. All right, so they are parallel. So I was calling this a parallelogram because it looked like one, but now by playing around with the angles, I've shown that they are parallel. So that's kind of a review of last week a little bit, some stuff we did there. All right, next. Let's pick this apart one more time. So, screenshot. I'm going to grab this again. And new page. All right, so this again is a quadrilateral. And the next part of the activity that I want to work on with you right here is what's the interior angle sum of a quadrilateral? Well, I have one in front of me, so let's play with it and see. Wrong page. There we go. So let's see, what do we know right now? Well, we have angle A over here. Oops, that's not a pen. So that's angle A repeated there. This one right here combined was a combination of angle B and angle C. Over here, I have angle A again. Over here, I have angle B. And over here, I have my angle C. When I go around this to try and say, okay, what are the vertex angles? And again, the only vertices that count here are the vertices of the combined shape, which is that one, that one, that one, and that one. A quadrilateral has 1, 2, 3 vertices. That's not a vertex of the quadrilateral because this line goes straight without bending from here to here. And when I look at the angles associated with each vertex, what do we get? We get these that I've outlined in green here. And when I put them together, that gives me angle A. And then up here, I've got the measure of angle B and the measure of angle C there. When I go over here, I have the measure of A and the measure of B from that one. And then I get down here and I get the measure of angle C. Did I get them all? So here's my first one, second one, third one, and then the fourth angle. And what happens when I put these together? Well, if I take A, B, and C together, what's that have to add up to? So that would be this group of angles here. And then over here, that's another group of A, B, and C for this quadrilateral. And this is kind of, in some sense, a random quadrilateral because I just took some triangle and put 3 of them together and it happened to make a quadrilateral. What's the sum of angle ABC? Anybody out there? Yes, that's 180 degrees. And why? Because angle A, B, and C came from a single triangle. And there's another 180. So what's the sum of all the interior angles, the vertex angles of this quadrilateral? So this quadrilateral has an angle sum of 180 plus 180, which is 360. So the question is, does any quadrilateral have an angle sum of 360? So we're going to test that out with one more example. So this quadrilateral has a vertex angle sum of 360 degrees. All right, so let's go to one of these pattern block things and grab another one. Come here, please. Whoa, try that again. That is hiding my tools. All right, so I have a few quadrilaterals here. I have this quadrilateral. I have this quadrilateral. There we go. I have this quadrilateral, and I have this quadrilateral. Now, in the previous activity, I asked that you find the interior angles of each of these. And so if you finished activity A, then you're going to have some evidence about what's going on with these. So let's just do a couple of them right now. And again, there's also this other one here that you can play with. And if you weren't with me Monday, I like this one because they kind of behave like I'm really pushing them around the page. And when they touch each other, they kind of move in funky ways, which I thought was cute. All right. Anyway, let's go back here. So let's see. The square, well, those are right angles. And we know a right angle is 90 degrees. And 4 90-degree angles adds up to what? A good day, 4 times 9 is 36. Put a 0 on there and it's 360. So I've got that as evidence right there. So I'm going to, let's see, add this to my workbook. All right, so what do we got here? We've got 90, 90, 90, 90. So here is 4 times 90 degrees, which is 360 degrees. So that definitely has a vertex angle sum of 360. This one right here, you could say is made out of 3 equilateral triangles, like this equilateral triangle over here. And this, if this is equilateral, it's also equiangular. A triangle is the only polygon that if it's equilateral, it has to be equiangular, or if it's equiangular, it has to be equilateral. That's not true of other polygons. For example, quadrilateral, this one right here is equilateral, that is an equilateral quadrilateral, and that is an equilateral quadrilateral. But this is not equiangular, and that is not equiangular. So this is the only one that's regular because it's equilateral and equiangular. So if this sucker right here has 180 degrees to share and each angle has to be the same, how big is each angle in this triangle? A response would be wonderful. I'm going to wait patiently for a response. Don't all speak at once, please. Or maybe you could speak at once. 60, thank you, Kayla. Yeah. So what I know then, because of the equilateral triangle, the vertex angle is 60 degrees in measure. That means this must be a 60-degree angle. That doesn't stand out very well. Let's write it on the outside. So that must be a 60-degree angle. This one must be a 60-degree angle. This one must be a 60-degree angle. That's a 60-degree angle. That's 60. And that right there is also 60. So this gives me a sweep of 120 degrees up there at the top. That gives me another 120. And if I take 120 plus 120 plus 120, oh, lied, plus 60 plus 60, what do I get? Well, 60 and 60 is another 120. 120 and 120 is 240. Another 120 is 360. So I get another 360. So far, the 3 quadrilaterals I looked at, I'm getting 360 degrees. That's supposed to be a degree symbol. This one right here is, again, 2 equilateral triangles. And so that means that angle right there is 120. That one is 120 because it's 2 60s and a 60 and a 60. So interestingly, these 2 quadrilaterals have the same vertex angles, but in a different order. Kind of cool. So again, 360-degree interior angle sum. Now, just because we found 3 examples, does that mean it's always true? Interior angle sum. Answer is no. There could be an exception to the rule. So we have evidence that it's 360 for quadrilaterals in general, but we haven't proved it. So I'm going to go off to Geogebra now for a quick experiment. Thank you, Giselle. All right, so if you haven't played with Geogebra, I recommend you do so now. There are 2 recommendations I have on the ones to play with. Don't go to start graphing. That gives you their graphing calculator. I don't recommend that one. But either under more apps on their homepage, the geometry app or the Geogebra Classic. So I'm going to record some videos later of me using the geometry app, but the classic one works good. And if you happen to look at my notes page, I link out to each of them for drawing polygons. And I think I'm going to go for demoing the geometry one, and maybe I'll get to the classic one. So I'm going to open the geometry one in a new tab here. I do have Geogebra on my iPad, but I find it rather painful to use, but it is possible. So here I have a polygon tool. And so I'm going to draw myself a quadrilateral, but I'm going to get a little wild here. I'm going to make a concave quadrilateral. All the ones shown in my notes at the moment here, these are all convex quadrilaterals. So I'm going to make a concave one, so it has to cave in on itself. So I choose the polygon tool here, and then it tells me what to do. Polygons at the bottom left, select all vertices, get back here, then the first vertex again. So just kind of playing around, 1, 2, 3, 4, back to where you started. So there is a quadrilateral. None of these lines are parallel to each other, and they don't appear to be congruent, so this is just a quadrilateral. It's not a rhombus, it's not a trapezoid, it's not a parallelogram, not a rectangle, not a square. It is convex, not concave. So I'm going to try again. And actually, after you make these, you can go to the Move tool, and you can move them around the screen. Or you can grab a point, and you can move that point. Whoa, check out that one. That's pretty. It's like a kite. Okay, a kite is a quadrilateral. That's not quite a kite. It would be a kite. There's a video on this in Khan Academy. If these two top sides are congruent and these two long bottom sides were congruent, then it would be a kite. I don't think mine are all congruent, so this probably isn't an official kite. But anyway, I wanted it to be convex or concave. So here's kind of concave. I'm just going to warp it a little more. And hey, that looks like the Star Trek symbol. Cool. The Star Trek symbol is a concave quadrilateral. Now, the reason I'm bringing this into Geogebra is because I can ask Geogebra to measure these interior angles for me. So I'm going to blow this up a little and do that. And if you are trying Geogebra with me and you have any questions as I play here, let me know. So let's see, I don't see a tool to measure angles here, so I'm going to click More and just kind of look through the tools, Measure Angle. Oh, let's try it. If I click on it, it'll usually tell me more. Select 3 points or 2 lines. Okay, let's try the 2 lines thing. So if I select this line and that line, hey, it gives me an angle, 41.3. Let's try that again. What if I select this line and that line? Okay, I'll have to move that to see what it is. Sometimes the things overlap and you got to grab the Move tool and then attempt to grab and move that number. Okay. All right. What's going to happen? Let's find that again. Angle. You can also select 3 points, but the order you select them matters. Let me just try that again here. So if I go A, B, C, it's going to try and find me angle B. If I do that backwards, C, B, A, what's it going to do? Same thing. Oh, that's interesting. They changed it. It used to be when you did it in the other order, it measured around the other way. All right, so undo that. Okay. So angle measure, let's get this angle here. Ah, I wanted the inside one. It gave me the outside one. Let's see, can I force it to give me the other angle? I can always subtract from 360, right? Because going all the way around is 360. But I want it to measure for me. Let's undo and try again. What if I do the point method? So angle, point, point, point. That's the wrong way. I want to go the other way. Escape. How about this? Point. Oops, I got to go back on angle. Point, point. Ah, it still wants to do that one. Okay, at the moment, I don't know how to get it to do the other one, so I'm gonna have to do some arithmetic on this in a minute. And then let's get this one over here. All right, so I kind of got the angles. Let's figure out what the angle sum is. And let's move them so we can actually read them. So put you here, and you here, and you here. I guess I'm gonna have to put you here. And then screenshot, what do we got? Is that really 360? New page. Magic pen, where'd you go? Let's see. I've got 41.3, and then I have 35.1. Now, I don't want that angle. I want this angle. So that means I have to subtract from 360. So I got to figure out what's 360 minus 107.3. But we are good subtractors. line up the decimal point and borrow, or we could use that equal additions. That was always kind of cool. So 0 minus 3 I can't do, so I make that a 10, and then I increase that to an 8. 10 minus 3 is 7. 0 minus 8 I can't do, so I make that a 10, and then I'm going to have to make that 10 an 11. No, I didn't have to do it that way. Make that 0 a 1. 10 minus 8 is 2, 6 minus 1 is 5, 3 minus 1 is 2. Okay, so this angle right here is 252.7. 252.7 and then 30.9. So 7, 8, 9, 10, 10, 0, carry 2, 3, 5, 10, 0, carry the 1, 5, and 5 is 10, and 3 and 3 is 6. That's a 16, carry the 1. Hey, it adds up to 360. Okay, so I have now done like 3 or 4 shapes, 5 shapes. All these quadrilaterals have an interior angle sum of 360. So I think it's getting pretty clear that it's got to be. So here's a way to prove it. If you draw any quadrilateral, so like this one right here, and then you dissect it by picking any vertex and connecting it to a vertex it's not connected to, right? So, ooh, it doesn't want to connect there. Oh, close enough. So this vertex right here was connected to that one and this one, but not that opposite one. So I connect to a vertex it's not already connected to. I have now broken this quadrilateral up into 2 triangles. And I know that the angle sum of this triangle is 180. And I know that the angle sum of this triangle is 180. And if you put those 180s together, you get 360. Okay, so the angle sum is always going to be 360 on a quadrilateral. So what I want you to do, and I did way more work than you need to, I was just trying to go out of my way to justify that to you. Come up with what you think the angle sum is, and then come up with some explanation of it over here. And then try the same thing on a pentagon. So I could build a pentagon with these pattern blocks here. So if I just take this guy and I stick it on top of that one right there, I've made a new shape. Let's trash these others for now. And let's copy that for a pentagon. So it turns out with the pattern blocks, you can build lots of other shapes. Well, we know a lot about this shape right here. We know the measures of all these angles. So this one right here is a 90-degree angle. That's another 90-degree angle. We know that this angle up here from our work with triangles is 60 degrees. And if I take 90 and 60 and put them together, that's going to be 150. And again, 90 plus 60 over here is another 150. And if we put all those together, what do we get? We get 150 for those, or let's just kind of summarize it. 150 and 150 is 300. And then we get 90 and 90 is 180. And then we get the 60 in there. So 0, what's that? 14, carry the 1. 1, 2, 3, 4, 5. 540. 540, 540. Is that special anyway? 540. Huh. Oh, this is kind of interesting. Check this out. I know 180 is a triangle, right? And 30 and 60 is 360. That's 2 other triangles. So somehow a pentagon is related to 3 triangles. Huh. Let's see about that. And draw another version of that thing over here. So it looks about like that. And then we have a little hat, cute little house pentagon. All right, so there's my little house pentagon right there. And I'm going to pull the same trick I pulled back here with this quadrilateral. I'm going to pick on a single vertex and watch what happens when I try to connect it. Oops, wrong button. Next page. So I'm going to pick on this vertex at the top. And this vertex right here is already connected. Pick a different color. It's already connected to that one, so I don't have to make another connection. It's already connected to that one. It isn't connected to this one down here. So I'm going to connect that there. And it's not connected directly to that one, so I'm going to connect it there too. Now, when I do that, when I focus on a particular vertex and I connect it to a vertex it's not a vertex it's not directly connected to, that makes a line called a diagonal. So basically what I'm doing is from one particular vertex, this one right here, I'm trying to make a star, if I connect its diagonals, then I've broken this pentagon up into 1, 2, 3 triangles, and I know that each of these triangles has an interior angle sum of 180. And when I put all those interior angles together for these triangles, it happens to match the interior angles of the original figure. And so 3 180s is 540. Okay. So you got a head start on this activity, so your goal is to try and finish it up. So we've got 180 for a triangle, we got 360 for a quadrilateral, and we got 540 for a pentagon. Does that pattern continue? Give me some evidence with a brief explanation. And then here's the big question. An n-gon means n could be 8, or n could be 7. Heptagon is a 7-gon, by the way. Or it could be 6. If we just, can we make a formula where we just plug in the number of sides and out pops that vertex angle sum? Okay, so that's the ultimate goal here. So you're gonna fiddle around for a bit looking for a pattern here, and there should be a pattern. 3, 4, 5, 6, 7, 8 sides. We want to generalize for n sides. So we're going to have a little formula with an n in it, where n represents the number of sides. We pop in a 6, and out pops the actual vertex sum, the vertex angle sum. All right, we need to quit any second now. Let's see. I strongly recommend you try Geogebra sometime soon. And I recommend the geometry app. The classic app is similar but different. They show a little bit more complicated stuff. So they've got this calculator you can view. They show the grid with numbers. That's all hidden from me in the geometry version, but somewhere there's a button here for me to turn those on if I really wanted to see coordinates. Let's see, I think that's, oops, what did I do? I'm drawing on this. I didn't know I could do that. How did I do that? Huh, that's cool. Show desktop. How do I make that go away? Uh-oh, what did I do? How did I do that? This is new to me. Pen, copy, no. Help, I've broken my, let's sure add it to a new page. Will it go back to normal now? Okay, I have something new to learn about my technology. Okay, I think I'm back to Geogebra. Sorry about the scribble on the screen. I do not know how to get rid of it. Oh, I do. I can just close this app. Quit. Okay, freaking me out. So I could say, hey, show me the axis, and I could say, show me the grid. And it'll, it didn't put it in there. All right, so there's some way to get it to make that happen. Oh, no grid lines, major. Okay. I wanted to see minor grid lines. So I could make the geometry one look like the other one, but I kind of like that clean view where they didn't show the axis and they didn't show the grid. The thing I like about this version though isn't this is the classic view of GeoGebra, isn't the fact that I can see this screen, the grid here, but it's the buttons are kind of easier to get to. Here's all the point type tools. Here's all the line type tools. Here's all the parallel perpendicular type tools and so on. So sometimes I like grabbing these here than looking through the lists over here. But we're all different. You can do all the same stuff here as you can in the classic, it's just organized different. So anyway, lately I've liked the geometry view. Last year I liked the classic view. All right, let's take a look at the next activity, and then I better shut up. So choose your own adventure. So either you're going to make a regular pentagon and another, like a hexagon maybe here with GeoGebra or on paper, or you're going to make me a cool pattern with a tessellation. And let's see. I'm going to attempt to do that with this pattern block thing. So I'm going to do the tessellation first quick, and then I'll come back here. So you got to kind of play around with the tessellation. Now, for the first part, hey, this is a quadrilateral, it's not a rectangle. I could just tessellate a bunch of these guys together, and you want to get them to meet. And so sometimes this one's a little hard to get them to meet right. So maybe I'll use the other one. The other ones kind of snap into shape. So let's trash you guys. So sometimes when I'm playing, I like the other one. Sometimes I like this one. And so I could easily tessellate these. They kind of slide together when I put them near each other if I get close enough to the edges. There we go. And so here I got a few of them showing, yeah, I can tessellate these guys. Could I tessellate those there? Yep, you could tessellate those too. Could I tessellate this guy here? It's a quadrilateral. Answer is, yep, that could be a tessellated quadrilateral. This one here, you have to be a little bit more clever because that doesn't tessellate, that doesn't tessellate. Sometimes you got to rotate the figure to make it tessellate. And so now I can tessellate some of those. So make me a small, so right there, that's good enough. Give me a screenshot of that. That would satisfy that first tessellation here. Oh, where the hell did you go? Heck, sorry. So that's part one of option two. I just tessellated a quadrilateral that's not a rectangle. With the blue example, or a couple more, I could do the red example. Semi-regular tessellation. There's a ton of examples here. You could try to replicate one of these examples with the pattern blocks. Not all of these are replicatable with the pattern blocks because the pattern blocks doesn't have some of these shapes, in which case you would try to draw it on paper if you would want to do one of these. What wouldn't be okay is if you just grab their image and say, hey, here's my tessellation. I want you to draw it or design it on a computer. And so I mentioned in this part that you might want to have a compass and a protractor, some scissors, tape, and glue, because you might want to cut out copies. You be creative, have fun with this. So this one is definitely the more creative one here. So you can color some things in. If you look at the example in the book, they tried to color everyone differently. So the book had a similar example to this one, but every other one was colored a different color. Like that was green, and that was green, to kind of emphasize the tessellation more. A quick example of a semi-regular tessellation here. Let's rotate that back. Semi-regular is where you take two or more polygons, and they don't have to be regular, by the way. You can tessellate irregular polygons, totally. And I can draw that in a sec if you want. But when I put those two together, I'm thinking, man, that looks a lot like that green triangle. So I'm going to grab that and put it in here. Oh, check it out. So maybe I could tessellate a bunch of these guys with an occasional green triangle. Okay, so here's me making a semi-regular tessellation. Now, question, is this really a semi-regular tessellation? I'm not going to answer that because I want you to double check in the book. The book gives a definition for a semi-regular tessellation, and if it doesn't meet that definition, even if it uses two shapes, it's not a semi-regular tessellation, it's some other kind of tessellation. So the question is, does this one meet the definition or not? I might have to tweak it to meet the definition. I'm not going to answer that question. I want you to check that out in the book. Book defines semi-regular tessellation in the tessellation example in the 1, 2, 3, 4, 5th example. They talk about what it means to be semi-regular. Okay. Let's see. All right, I'm going to now show just a little bit. If you're good on the tessellation for your version, feel free to check out. If you don't want to use a program like that to do it, you could, again, draw these on paper, in which case you're going to want to use a ruler to be careful about it, and maybe a compass or protractor. I'm going to demo one of these here. So let's see, method 1 or method 2. I thought method 2 was cuter. And I'm going to go show you why. So it says mark a center point and an endpoint for a radius. Okay, so I'm going to split my screen and do this. Let's get Geogebra. And if you want to, by the way, you can download this file. if you did something in GeoGebra. And then you could either send me to a GGB file, means I can go upload it into GeoGebra to see it. Otherwise, you could send me a PNG, SVG, or PDF. So I recommend using one of these top choices to send me the file. I'm just going to go new and wipe this one out. Don't save, please. And I'm going to try and follow the directions that I give here. Okay, so it says draw a straight line segment with a starting point and an end point. And I show this the straight line tool, the segment tool right there. So I'm going to draw, oops, what happened? Why did you stop working on me? Segment, there we go. Click, oh, that has to be visible to draw it? That's weird. Okay, fine. So I draw my segment. All right, so there's my segment. Next, oh, I wanted to do this one. I lied. Damn it. I mean, darn it. Excuse me. Undo. Because this I thought was the cuter one. Mark a center point and an end point and draw a circle. Okay, and I'm recommending using that tool, circle with a center. So I go boom and boom. So now I have a center point marked and I have a point on the circle marked. And these directions are in the book, written slightly different. Mark another point on the circle using the proper central angle with a protractor, and the protractor is that tool right there, and that would be angle of a given size tool, right? See, they match. So, but oh, what size should the angle be? Well, let's see. I want to do a pentagon, and this is the central angle for a pentagon. The central angles always add up to 360. So this would have 5 central angles. 360 divided by 5 is what? 360 divided by 5. So this is a little review from, this was covered, I think, last week. Oh no, maybe it was this week. 72 degrees. Okay, so I need to measure a 72-degree angle from this radius right here. So then to do that, I click on the outer point first, the inner point second, and it says, how about a 45-degree angle? Counterclockwise. So that means it's going to go up from point B. And I would say, no, leave the degree symbol, but put in a 72 if you're doing a pentagon, and then say, okay. So there's my 72 degree angle from B to B prime there. All right, that's step 2. Step 3 says use a compass to repeat the distance. On GeoGebra, the compass is the circle with a point tool. And that was that first one I had right here. So what I do next, will you please work for me? Ah, darn you, GeoGebra. Okay, make the screen big so we can see it better, and move you over here. Apparently, if you hide this, you get the move tool. I want that tool. All right, so what I'm going to do is I'm going to make that the center and that the radius point out. And then I'm going to repeat that, but the other way. I'm going to make this the center and that the radius point. So now what I have is I have 2 more points here and here that are the same distance as these 2 are apart, because I pick circles with the same radii. And that's what compasses are used for in constructions in geometry. So next I need to mark those 2 points by finding where they meet. And I made a note back here, where'd you go? Right there, that you should use the intersect point tool to make that happen, with that little image. So back here, I need to find the intersecting point tool. And again, when you first get to this, you're shown very few things, right? Only those there. So I have to click more. And I don't see the intersect tool yet. So I have to hit more again, and then it's back up here, intersect. And all you do is point to the intersection, and it tells you what point that is. And then I do the same thing here. And then I just want to repeat that process till I have points all the way around that are equidistant. So back to the circle. So this again acts as my compass tool. And I'm going to go, let's see, this is the center, and that point is the radius. I'm going to do the same thing over here. This is the center, and that point is the radius. And I'm almost done. I have to find that intersection again. Point and click. Wow, they met at the same spot. And again, they should have because with 72 degrees, I should be able to go around 1, 2, 3, 4, 5 times perfectly, because 5 times 72 is 360. The last thing I want to do, now I don't have to because I do have a regular pentagon here, right? I can go in here and say, hey, polygon, click, 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 click. I have a perfectly regular pentagon here, okay? They each have the same exterior angle measure. What is the exterior angle measure? Sorry, interior angle measure, vertex angle. What is the measure of the interior angle of a regular pentagon? That's an excellent question. But just to make it prettier, I'm going to add this last circle, because then I get this cute pentagon flower, which I've always been very fond of flowers. Oops, wrong spot. Escape here, and then out to, oops, circle tool here and here. Isn't that beautiful? Check that out. So I have a regular pentagon following those directions, plus I made a pentagon flower out of circles. That was kind of fun. All right. So that's more than enough for now. Too much fun with geometry. Mind is about to explode. All right. More than enough to keep you busy this week and probably into next week. Next week is a relatively light week, so we can continue this stuff next week if we need to. If you have questions, if you get stuck on something, send me a message in the inbox, or email me if you like to email. And I'll get back to you when I can. If we need to get together for another Zoom chat, I'm more than willing to do that on Thursday, Friday, Saturday, or Sunday, if you need help with stuff. Otherwise, we have the next session is Monday at 3 o'clock. Your goal in the intervening time is to do your best to try these activities and submit something, and I'll link this work, and the Khan Academy assignments. And remember, for that choose your own adventure, you either are going to draw a couple of polygons, or you're going to do those 2 tessellations, but you don't have to do both. And it's important you read in the book the definition for what is a semi-regular tessellation, because it turns out there's like a gazillion kinds of tessellations. And a semi-regular one has a special definition in the book. It explains it. If you don't get the book's in explanation, then send me a message and I'll try to explain it a different way, and whether that one I made over here meets that definition or not. So that's it for now. Good luck. I hope your lives are going reasonably well. Don't let your guard down, because this COVID thing ain't over yet. So stay safe and keep your loved ones safe. I'll see you all in the near future. Please get in touch if you have any questions. Bye-bye.